Hi, this is a brief introduction to Stateright, which is a framework for building and verifying distributed systems. It's based on this ebook called Building Distributed Systems with Stateright, which is accessible at the URL here. And I will also paste a link to that in the video description. So in this screencast, we're going to follow chapter 1 of the book, and I'll also go in some additional directions from chapter 1 just to kind of fast track you into some of the other concepts that the book explains later. So the strategy behind the book is to really just kind of jump right into the code and then explain distributed systems concepts as you walk through the code. So we'll go ahead and follow the example here. So we're going to make a directory for getting started, and we're going to cd to that directory, and we're going to start a new Rust project in that directory. Then we're going to set some dependencies in our cargo.toml file. And we'll just go ahead and copy paste the source code as well. Let's see. Oops. Set paste. And let's try this again. All right, so here we've got the source code for the first chapter. We'll save that, and let's go ahead and test out the system. So I'm going to use cargo run to build. Build's almost complete. All right, so now we have a very, very simple actor system running. In this case, it's a single actor on port 3000, localhost port 3000. So we'll load up another terminal, and in this terminal we are going to run a tool called Netcat on port 3000 of localhost. And this lets us send UDP messages to this particular actor. So the first thing we'll do is we'll send a GET message, and this number here is the request ID. So if we send that, the actor replies back indicating for request ID 0. I'm replying to request ID 0, and the value currently is the question mark, which is sort of the default value of this actor. Then we can send a put message, which has its own request ID and then a value that we want to put. Let's put X. We get back a reply indicating, yep, I got the value. And now if we resend that GET, let's say the request ID is 2, we get back the value X. So this actor is kind of like a key value store, but it's not replicated, and it doesn't have really a notion of multiple keys. There's really sort of one key. And so this actor, in some senses, is effectively a distributed register, distributed unreplicated register. All right, so that is interacting with the sort of actor system in a real world scenario. Now what we're going to do is quickly look at the we'll quickly run the test. So we have to go to getting started, and now we'll run the test. All right, so the test here is actually asserting a bug in this actor implementation, which is that the actor is not linearizable. Linearizable is a term that effectively means that the actor doesn't behave in a way that you might expect the semantics of the that it's emulating. So in this case, it's emulating a register. So if you were working with a register on a single-threaded system and you wrote a value to that register and then wrote another value, you would expect the register to then return, if you did a read, the latest written value and not like a stale value, for example. That's an example of returning a stale value would be an example of a behavior that is not linearizable. And the book explains this in more detail, but I won't take any more time to discuss that right now. The source code that we copied, here's the test that gives an example, gives a counterexample for linearizability. We're actually going to change this to kind of show you how you might use it in practice. So in a real distributed system, you would not have a test asserting that there's a bug. Normally you would just have a test that asserts that bugs don't exist. So you would have a test that says is linearizable, for example, and in that case you wouldn't expect it to fail in any particular way. You would actually just call an assert properties method, which verifies that the system adheres to all of the properties that we expect, and linearizability is one of those properties. So here we'll go ahead and save this, and now we will rerun the test, and this time we're going to expect the test to fail because it will find a behavior that's perhaps unexpected. So the test fails. It indicates that there is a counterexample of linearizability, and it's this sequence of steps. So the client had already sent a message to put the value A, and that message gets delivered to the server by the network. The server then indicates to the client that it accepted that put. Then the client sends the value Z. And then concurrently with sort of the client has sent the value Z, it's been received by the server, so the server persisted the value Z. And it replies back to the client, but the client hasn't gotten back that message. It hasn't gotten back the OK just yet. Instead, the next step is that the network redelivers the first message, and I'll explain that in just a moment. So after the network redelivers the first message, the network then delivers to the client the acknowledgement that the put succeeded. Then the client does a GET request, and it gets back A, which is the first value that it put, which is not necessarily what the client expected. So you might say, well, why did the network redeliver that first message? It turns out that networks are designed with redundancy, and there's various systems that can cause a network to redeliver messages. And so this is something that any sort of UDP network, for example, or even a TCP, even if you're running TCP, it's still possible that particular messages could get redelivered, although TCP does take some precautions to try to minimize that. It's still possible. And Stateright is basically pointing out that the actor system that we wrote, even though it's a very simple actor system, which is namely you have an actor, it starts with the value question mark. There's two different kinds of messages it can receive. If it gets a put message, it resets its state to match the value that was put, and it replies indicating that it accepted the put. Or if it gets a get message, it just returns back the state that it currently has. This double dereference right here is simply because Stateright uses a copy on write for the state, and that's a mutable reference to a copy on write. So, or rather a clone on write container, and so we have to dereference twice. First to dereference this reference to this mutable reference, and then to dereference the clone on write container to actually get the internal state to get that internal state. So and then that state is copyable, and so we don't have to we don't have to call clone or anything like that. So you might not have seen, like if you were to glance at the code here, you might not realize that, oh yeah, this actor is extremely simple, and even this simple actor has some sort of bug. If you were expecting it to behave kind of similar to what a local register, how a local register might behave. The next thing I want to show is how to sort of the debugging tools that are available on Stateright. So we'll come back here, and instead of spawning a depth first search of the system, we're going to run the Explorer view, which will actually do a breadth first search, which in turn gives us shorter counterexamples, and also gives us kind of a UI that we can use to explore the system. So we'll rerun the test. Whoops, cargo test. And now the test will suspend because it's waiting on the server. And so if I come over here and I run localhost 3000, you can see that this is the Stateright Explorer UI. Here we have model checking status. Here are interesting things that the model checker has found, and then path just represents a series of steps that the system can take. And so if we click on linearizability counterexample, you'll see here that the system says that the client sends the value put, and then to the server sends put OK, the client sends put again, the server says put OK, the second put has the value Z, the first has the value A. And then what happens is the network redelivers the initial put message, and overriding the value Z with A again, and then we have this get that returns back A, which is not expected, and so that's an example of linearizability being violated. So another interesting example is you might want to verify that the system can choose a value, because you can protect against linearizability violations by just ignoring every message, which that's also not a very useful implementation. So there's also this notion of non-triviality checks. So you can indicate that a value, it should be possible to choose a value, in which case the model checker will find that too. And if there's no way to choose a value, then the model checker that's built into Stateright will detect that. So that's the basic UI. I should probably also walk you through sort of how this path gets generated. So first we have this state where the system hasn't even initialized yet. Turns out there's only one initialization option. So there's the way that this model is written is that there is no non-determinism with initialization. And here you can see that there are two actor states. Actor index 0 is the server, actor index 1 is the client. The client has sent one operation, and it's waiting on request ID 1. We'll skip over the linearizability tester here and the timer information and just look at the network. The network here is modeled as a set of every message that's ever been sent, because the network is free to reorder messages, the network is free to redeliver messages, and so a set, it turns out to be a pretty good model of the semantics of most practical networks under sort of worst case scenario. And then we have this notion of next steps. So these are the things that can happen next where they're not like a complete no-op. So if it's possible for something to happen where the actor would completely ignore it, then it's not even going to show up in here. But if the actor will respond to particular events, then you'll see those here. So the only thing that can happen initially is that the message that the client sent gets delivered to the server. So in that case, you see that here in this message passing diagram, that client 1 sends a put message to the server, which is actor 0, and you get a summary of the delta here. So the recipient, which is the server, returns back a put OK message. Its new state is A, its old state was question mark, and now we have two different things that can happen. Either the server can receive the original put once again, or it can, or the network can deliver the OK to the client. And so we'll see what happens if we do an OK. So now the client gets an OK, and maybe now you've got more non-determinism here. Maybe the network redelivers A, maybe it redelivers A again, but then the client sends a, well, now the network delivers the second put from the client, which is when the client got the OK, it then put a message on the network to to put the value z, and so you can see that in this sort of behavior diagram. So these can be kind of useful to see the relationship between different steps. So I think that's pretty useful. That's probably enough for this initial introduction. I recommend looking at the book. There are currently 3 chapters that walk you through sort of increasingly complex use cases, and there's even exercises that you can follow. So take a look, and please reach out via GitHub and or Discord to let me know what you think. All right, thanks.